Hello and welcome to the fifth lecture in this series on EcoModernism. EcoModernism is the philosophy that the best path forward for humanity lies in embracing technology to help us clean up our planet, rather than demonising technology for its role in creating the mess in the first place. Today we're looking at what many people consider a key piece of the future energy mix, which is energy storage. Traditionally, energy has been stored in fuels like coal and petrochemicals, which we can burn when we need them. But with the rise of electric power and the necessary removal of all our carbon-polluting processes, we've separated the storage medium from the fuel. Now we need to store electricity itself in our cars and our homes. And more importantly, we need to work out how to store the energy generated from renewable sources, such as solar panels and wind turbines, so that we can continue to power our homes when the sun isn't shining and the wind isn't blowing. So, energy storage is hugely important. Indeed, it's a vital piece in the puzzle that we'll have to solve in the next 10 to 15 years. But currently the solutions we have all come with their own sets of problems and challenges, and we need to take those into account. It's definitely not guaranteed that we will be able to build out our storage infrastructure as quickly and effectively as we need to, and the demands on our national energy grids in the meantime will be significant. Let's take a look at the issues involved. I covered renewable sources of energy in an earlier lecture, and it should be clear to everyone listening to this that renewable energy generation is going to increase a great deal over the next couple of decades. However, as I mentioned in that earlier lecture, renewable energy comes with the inherent challenge that it can't necessarily generate power when you need it, but it only generates when the conditions are right. That means solar only operates during the day, and mostly when the skies aren't cloudy, and much more in summer than in winter. Wind power generates when there's wind, which is usually more in winter than summer, but can be at any point in time, and the winds may be too still for days or even weeks at a time. More than that, some places are just sunnier or windier than others. This all causes a problem for conventional electricity grids, which are designed around the concept of having a solid baseline supply that provides the bulk of our energy needs. And then we add peaker plants, which are usually very quick to switch on or off, that provide the peak demands when required. That might be in the evening when people get back from work and cook dinner, for example, or during times of extreme cold or heat when central heating or air conditioning are used. The base load has historically been generated by coal or nuclear power plants, which are steady and reliable, but slow to start up or shut down. The peak demand was usually satisfied by gas turbines, which can be spun up or down as required. But the addition of renewable energy changes that mix considerably. Solar power can fluctuate enormously on a minute-by-minute basis, or even on a second-by-second basis as clouds move overhead. Gusts of wind can cause wind turbines to speed up and generate significantly more energy for brief periods of time. Though you can shut wind turbines down if the wind is too high, you really don't want to have to do that, as you're then wasting energy generation and reducing the value of your turbines. This rapid variability and unpredictability are the two most significant challenges for the electricity grids when adding a significant fraction of renewables, beyond 20 or 30% or so of the total energy mix. The problems are amplified more and more as the proportion of renewables increases. So any good storage solution for our grid must provide the ability to even out fluctuating production and also provide the ability to store energy in times of plenty to use in times of scarcity. The technologies used for these two tasks are sometimes the same, though some are really only suitable for one or the other. It's a question of using the right tool for the job. Let's take a look at the most common technologies used to store energy and examine where they might be of use. Humans have been storing power using water for centuries, ever since the first dam was created, with a gate that could be opened or lowered to let water through, and a water wheel at the other end. Modern pumped hydro storage is barely any different, though of course the scale is vastly larger. We are familiar with hydropower plants, where water naturally flowing from a high location to a low location, usually in a river, passes through a set of turbines on the way, turning them to generate power. Essentially, this is extracting energy from the gravitational potential energy that the water has when it's stored at a higher elevation. Pumped hydro is a form of energy storage that takes advantage of the fact that this process works both ways. We can generate power by allowing water to flow from a high location to a low location because it's losing gravitational potential energy, But we can also spend energy to move water from a low area to a high area, transferring that energy by use of electric pumps from electricity to stored gravitational potential energy. Then when the energy is needed, you open the gates and the water flows through to generate electricity. There are several plants operating on this principle already in action, including this one on the Canary island of El Hierro, which has allowed the island to switch to more than 50% renewables, primarily wind turbines, the excess power from which is used to drive the pumps. The largest pumped hydro storage plant is the Bath County Pumped Hydro Storage in the United States, with a 3 gigawatt generation maximum and a storage capacity of 24 gigawatt hours. Located on the border of Virginia and West Virginia, it stores enough energy to power roughly 3,000 homes for an entire year. Other enormous storage facilities exist in the US, in China and Japan. Overall, China leads the world in storage capacity here, with 32 gigawatts of pumped hydro storage. Pumped hydro is great because it uses tried and tested technology. We've been building dams for millennia and powered pumps for at least a few centuries. None of this is rocket science. But of course, as with hydropower itself, the main restriction here is geography. You have to have a country with lots of mountainous terrain adjacent to much lower terrain, and you have to not mind destroying hundreds of hectares of that beautiful mountainous terrain by flooding it and building huge concrete structures to turn it into a giant lake. This is environmental destruction on a grand scale. We could argue that the cure might be better than the disease, but the cure isn't pretty, and there are definitely other cures that we might want to consider instead. Pumped hydro, however, is fairly efficient, roughly 80% round-trip efficiency. That means that if you have 100 megawatt hours of energy you want to store, and you use it to pump water into a pumped hydro plant and then run the water back down to generate power again, from that 100 megawatt hours you get back roughly 80 megawatt hours at the other end. The remaining 20 megawatt hours is lost, primarily as heat. The principle behind pumped hydro storage is that we can store energy by imparting gravitational potential energy to a large mass of water and later convert it back to electricity. There are other ways to do this that don't involve requiring mountainous terrain or destroying beautiful valley scenery. We can store energy using the physics of gravity and the movement of large quantities of mass in multiple forms. It doesn't have to be water. And of course there are other ways of storing energy by moving around large masses, because when you set a large mass in motion, you give it kinetic energy, which can also be used as a store. One way to duplicate pumped hydro but without the dams and reservoirs is to create the height difference yourself. All you need is two regions, one of which is significantly higher than the other. So there are two ways to go here. Either you build the power station at ground level and build up above it, or you build a power station at ground level and dig down below it. Both are plausible. In fact, both have working prototypes. The company Energy Vault is aiming for the first solution, building upwards by expending energy to lift heavy concrete blocks upwards, stacking them into giant towers. Then when the energy is required again, you simply pick up a block at the top of the tower and allow it to drop back to ground level, converting its gravitational potential energy into electricity. It's not the most rapidly responding source of energy storage, but it is one of the most stable. Barring serious earthquakes, and of course you don't build these things in earthquake-prone areas, you can pretty much store energy for as long as you like. And the company reckons they can store tens of megawatt hours of energy with the ability to generate between 4 to 8 megawatts of continuous power. Of course, this is also easily scalable. On the other hand, the company Gravitricity is going in the opposite direction. Their aim is to repurpose abandoned mine shafts and get energy by dropping large weights of up to 5,000 tons downwards into the ground. Then you expend energy to pick them up again. Here the height differential should be much larger, with many mine shafts being hundreds of meters deep, maybe even over a kilometre in some cases. The facility is able to generate up to 20 megawatts of electricity, with storage of roughly 10 megawatt hours. They reckon they can respond in less than a second, making it responsive enough to handle grid demands for which we might otherwise use peaker plants. Round-trip efficiency of both of these techniques is roughly the same as pumped hydro storage, something like 80 to 90%. It's not brilliant, but it's not terrible. But again, they can store energy on large scales with very little loss. You lose a bit by moving the masses around, but once they're lifted up high, they can stay there indefinitely, and they don't lose the energy they have, unlike with other storage mechanisms where the energy is gradually lost over hours or days. One of those other ways to store energy using physics is to use flywheels. It takes a lot of energy to spin up a heavy flywheel, so doing so is a perfectly acceptable way to store energy. The only problem is that they tend to slow down automatically over time because of air resistance, so you'll need to store them in a vacuum with super efficient low friction bearings. The efficiency for most of these systems is 90% round trip. They can react very quickly to changes in demand, and they don't need any expensive raw materials, or indeed any precious metals or toxic chemicals. They can potentially last forever, though the bearings will degrade over time, but the bulk of the apparatus will likely never need to be replaced. They do have some rather dangerous failure modes, of course, but I would argue they're no more dangerous than a battery fire or a hydro dam breaking. Their main weakness, though, is that they tend not to be able to store energy for more than a short period of time, due to energy loss through friction. Superconducting magnets might help out here and might reduce energy loss to just 5% per day, but most flywheels lose significantly more than this, and superconducting magnets are hardly practical. I think flywheels are likely to remain a niche use case, but there are several working installations that have been very successful for short-term storage and load balancing. Now we come to what most people think of when they mention energy storage, the humble battery, which has become something of a superstar in the last 2 or 3 years. With the price of a lithium-ion battery nearing the important mark of $100 per kilowatt hour, they are fast becoming the preferred method of energy storage. They have lightning-quick reaction times, reasonably good energy retention, losing only roughly 1% per week, and an extremely high round-trip efficiency in excess of 95%. There are now some well-known examples of large battery energy storage solutions, perhaps the most infamous being the Hornsdale Power Reserve, or the Tesla Big Battery in South Australia. This battery was famously built within 100 days as a bet with the energy company Tesla, headed by eccentric billionaire Elon Musk. Eventually the giant storage system cost 90 million Australian dollars for 129 megawatt hours of storage with a maximum output of 100 megawatts. It has since been extended to 194 megawatt hours of storage and 150 megawatts maximum output. That capacity would power roughly 10,000 homes for a day. The battery is primarily used to store power from the neighbouring Hornsdale wind farm, and it has already comfortably paid for itself, not only by storing excess wind power and avoiding having to switch the turbines off in times of high production, but also by helping to control the grid frequency by patching up mismatches between the energy supply and demand. So batteries are already being used, and they're already paying for themselves, and they are definitely an amazing proven technology. So why all these other slides about alternative technologies? Why not just use batteries for everything and the problem's solved? Well, yes and no. There are 3 major issues with battery storage. Firstly, we can't produce them fast enough. Secondly, we may not have enough resources to build as many as we need. And thirdly, those resources are only obtainable by digging up and ransacking huge chunks of the planet's surface. Let's take those in order. Firstly, how many batteries will we need to build to deal with a grid substantially powered by renewables? Well, that's a tricky question because it depends which renewables and where we build them. We could get something of an idea by estimating that we might need to store, say, 10 days worth of energy. Let's assume that we can somewhat cover our bad days by importing power from abroad, but we should have to size a battery to cover periods in the winter where the skies are dark and there's no wind. 10 days sounds like a decent guess to me. It's probably not out by more than a factor of 2 or 3. So what would that take? I'll work out the figures for the UK, which has a population of roughly 65 million, so you can scale this by whatever the population of your home country might be. UK electricity consumption is roughly 800 gigawatt hours per day, which is 8 terawatt hours for 10 days. That would require roughly 40,000 battery installations the size of the Hornsdale Power Reserve. Let's say we can hit the magic number of $100 per kilowatt hour, which is probably fair given the scale of batteries required. And let's say that the installation costs are all zero on top of this. That battery capacity would therefore cost $800 billion just for the UK. Oh, and the annual battery production of the entire world is currently roughly 300 gigawatt hours, so creating 8 terawatt hours of storage for the UK alone would take 27 years of the world's entire current production, and that's assuming nothing else was used for cars, buses, phones or other consumer electronics. And that is just the UK, which is less than 1% of the world's population. Also, it's just looking at our current electricity usage, not our current energy usage. Once we convert all vehicles, heaters and all industrial processes from oil and gas to electricity, we'll increase our requirements considerably. Energy use in the UK is roughly 6.2 terawatt hours per day, so it's 8 times what we use just in electricity. All of that will have to change to electricity eventually, which gives us another factor of 8 on the storage, and that's a heck of a lot of batteries. If we want the entire world to be powered at UK levels, then we will need the entire world's supply of battery production for thousands of years at current rates. And can I remind you, by the way, that we have to do this completely in under 30 years to avoid the most catastrophic effects of global heating. Of course, the developing world won't reach UK levels of power usage by then, but they will be well on their way. And yes, I know battery production is increasing at a ridiculous rate. It will probably increase by a factor of 5 between 2020 and 2030. But that still means that producing enough batteries for the UK alone would take 5 or 6 years of the world's entire battery production. And that's assuming nobody anywhere in the world wants any electric cars or laptops or phones. So that's point 1. I spent a while on it because it's important. But to continue the calculation, let's see how much lithium this giant battery storage project would take. The remaining lithium reserves for the entire world are around 50 megatons. That's 50 million tons. I checked the Tesla website and discovered that Tesla batteries have roughly 1 kilogram of lithium per kilowatt hour of storage. So to make 8 terawatt hours of storage for the UK, we would need roughly 8 megatons, 8 million tons of lithium, or roughly 16% of the Earth's remaining supply, for much less than 1% of its population. We would need roughly 10 times more lithium than remains on Earth to create all the batteries we need for the entire world. And again, remember that this is just the current electricity usage. We need to multiply that by a further factor of 8 or so to get the total energy consumption, all of which will have to be converted to electricity, all of which will need to be stored in batteries. And finally, to wrap up, point 3, lithium mining is, like many other types of mining, dress it up however you like, it's a dirty business that destroys vast amounts of pristine wilderness. Lithium processing involves extremely high temperature kilns that take a lot of energy and vast baths of scalding hot sulfuric acid. It's hardly a tree-hugging process. And batteries degrade over time, meaning they lose capacity, especially when being charged and recharged at high power over and over. Nobody knows what the operating lifetime of the Hornsdale battery will be, but when it loses a significant amount of capacity, it will need to be disposed of. That may be in 20 years, or it may be in less than 10 years. We don't really know. Battery recycling is already very promising and will no doubt get exceptionally good over the next decade, but it's still another cost that takes time, it takes resources and, of course, more energy. I don't want to make it sound like batteries are a bad idea. They're not. They're vital. Batteries allow electric cars, which are the future of transport. I own an electric car and I love it. I'm contemplating a home battery storage system. It just makes sense for me. But building the occasional home battery to buffer up the odd bit of excess solar power is not the same as providing backup and storage for an entire nation, or the entire world. Batteries are great, but they can't be the entire solution. One other way to store up energy from excess renewable generation is to store it in chemical form. And one way to do that might be to create an alternative green fuel using the excess electricity. Perhaps hydrogen. Hydrogen is a very light gas which can be burned to generate heat directly in converted gas burners, and can also be converted to electricity by means of a fuel cell. This is a device that takes in hydrogen and reacts it with oxygen present in the air to produce electricity plus heat and water. It's a perfectly clean fuel with zero carbon dioxide involved. Much has been made of the hydrogen economy, though I think now the general assumption is that its actual uses are probably rather more limited than was first imagined. However, hydrogen remains a very energy-dense fuel, and could possibly therefore be a good candidate for powering carbon-neutral aircraft, and maybe heavy goods vehicles. Given the problems with providing enough batteries in the timescales available, we ought to keep every possible alternative on the table. Most hydrogen today is mainly produced in a dirty process that involves extracting it from methane and belching out loads of carbon dioxide. But green hydrogen produced by electrolysis of water using excess electricity from renewable power sources, has zero carbon footprint and could genuinely be used to power a range of devices. As such, it's sort of an energy storage technology because we're taking excess electricity, using it to create hydrogen, a process which takes in a lot of energy, and then storing that hydrogen until we need to convert it back into power. I guess the storage technology here is really a large pressurized tank, which is hardly complex futuristic technology. And hydrogen can be stored for years or decades, again with very little loss. So hydrogen is a promising way to soak up excess wind power, say, and it has plenty of usage from domestic cooking appliances through large vehicles, even ships. Hydrogen-powered houses are popping up all over the world, with oversized solar arrays storing their excess generated electricity over summer by generating hydrogen and storing it for the winter in large gas tanks. The main drawback of converting electricity to hydrogen and then back to electricity, however, is the terrible efficiency. The electrolyzer that converts water and electricity to hydrogen has an efficiency of roughly 60 to 80%, but then the power cell perhaps only 50%. Giving an overall efficiency of the entire process of between 30 to 40%, which is pretty terrible. But having said that, if you have nowhere else to store the excess electricity, then 40% of something is better than nothing. It's better to have your wind farm running and store some of the energy, even in an inefficient way, than it would be to just switch the wind farm off and waste the power entirely. Also, we ought to mention that 30 to 40% is still much better than the best combustion engines today, the majority of which typically get 20 or 25% efficiency. So there is that. The final technology I want to cover here is actually one of the least well known, but one of the most promising. Any process that's reversible and takes energy to perform can be reversed and will therefore release energy when it does so. The British company Highview Power has developed a way of storing energy efficiently using cryogenic storage of liquid air. They cool down incoming air and liquefy it. They store the heat energy extracted, plus the cold liquid air, in standard off-the-shelf pressure vessels. Then, when the energy is required, they reverse the process and expand the liquid air into a gas to generate electricity. They have started building their first commercial plant near Manchester in England, which should store 250 megawatt hours of energy and can produce a maximum power of 50 megawatts when required. The project will cost £85 million and will store almost double what the Tesla battery in Hornsdale stored, at least before its extension. The cost of £350,000 per megawatt hour is 10% less than the Tesla battery, which cost £380,000 per megawatt hour. And that's the first commercial plant of its type. Further plants will certainly benefit from economies of scale and the knowledge gained building the first one, and it uses commodity components, not rare earth metals. The response time obviously isn't as good as with a battery, so that changes the applications that it can be applied to, but it is definitely extensible and shouldn't degrade over time like current generation lithium-ion batteries do. Highview reckon their plant will have a lifetime of over 30 years. The energy storage density is roughly 300 megawatt hours per acre, which is only about 10% less than Tesla's latest and greatest battery technology. So when the Manchester project comes online in 2022 or 2023, then we'll have to see if it lives up to expectations. The only weak point here is the round-trip efficiency, which is apparently about 70% compared to 95% for batteries. Obviously that means a lot of energy is wasted, which isn't great. As this is new technology, then it's possible that scientific research will be able to nudge that wastage down gradually over the next decade or two as Highview and other companies perfect the technology. So this is definitely one to watch. In summary, we have lots of technologies for storing energy, and none of them alone gives us a complete answer to the puzzle. Each solves different parts of the energy storage requirements that we're likely to have over the next few decades, and even taken together they still fall significantly short of what we'd need to be able to produce to move to a renewables-dominated energy grid. Not only that, but most of them have significant environmental problems of their own. Again, climate change probably is more important than those other concerns, but it doesn't mean that they're entirely negligible. Energy storage is difficult. It seems like lithium-ion batteries are a silver bullet, but we've seen that they cannot be because we simply can't produce enough of them fast enough. No doubt technological progress will help over the next 10 years. After all, the financial incentives for developing a good energy storage process are now enormous, so there's a lot of people working on it. But as of now, there's nothing we currently have that could fill the gap that needs to be filled. This is partly why I recommend that we continue to develop innovative Generation 4 nuclear reactors, as well as nuclear fusion plants, which will be able to provide the constant baseline load that our society requires, especially in times when the renewables don't provide enough power, for example, during winter when it's dark and there's no wind blowing. And probably we should also be working to move as fast as possible off the most polluting forms of power generation, especially coal, and onto much less polluting but still bad forms of generation like natural gas. It's not a pleasant answer, but it at least moves us in the right direction until we can wean ourselves off dirty fossil fuels entirely, as the technology for storage will improve over the upcoming decades. Thanks very much for listening. I hope you continue to listen and join me on this journey through the world of EcoModernism. Next time we'll look at carbon capture and storage and examine the claims that we might be able to make existing sources of power carbon neutral, or even that we might be able to create a carbon negative energy source. How true are those claims, and how far can we take carbon capture and storage systems in the time we have left? I'll see you next time.